This is 3.2, day 2 continued. We're going to look at residuals and residual plots. Make sure you have your handy dandy calculator for you on these notes. I got mine here on the computer. Everything else, as long as you have the notes in front of you, should be good. So we're going to start off with actually making an LSRL, a least squares regression line. We're going to use some data from McDonald's and their beef sandwiches. So based on their carbs, we're going to be able to predict the amount of fat in the sandwich. So we're going to calculate a least squares regression line using technology, our calculators, and then we got to make sure to define the variables that we use. So let's go ahead and enter these in L1, the carbs in L1, and enter the fat in L2. So usually we enter the X, the independent variables in L1, the fat goes in L2. So let's go ahead and do that now. So I go to Stat and Edit, and I've already got mine entered, L1 and L2. Should be 9 total entries for each one, if I did it correctly. So enter these into your calculator like so. If you haven't Inspired and you don't know how to do this yet, there is a guide in the back of the book also. Okay, so once you got these entered, you're going to hit Stat, Edit, not Stat Edit, Stat Calc. We already did Stat Edit. Go to Stat Calc. There we go. Stat Calc, and then we want linreg. So the fourth one down there, that's linear regression. So that'll give us our equation. So go to the fourth one. That's linreg. And then you want to do the list that you used. The X list was L1, the Y list was L2. So we're going to go ahead and calculate these. So go down to calculate, press enter. Boom, there it is. So our slope would be A in this case. So that's 0.335. Our y-intercept is B, 11.814. We'll go with 3 decimal places here. All right, so that's our line. So using our calculator, we came up with this line. And also this is on page 171 if you need another tutorial besides the one I just gave. So let's go ahead and write the equation of the line. So y hat equals our slope, which is 0.335, plus our y-intercept, which is 11.814. So we have a slope and y-intercept. And then, so right now this doesn't have any context to it. Someone reading this would have no idea which variable represents which. So that's why it says you make sure to define your variables. So we need to say where y hat represents what. Well, our y values was fat, so the hat means that's the predicted fat, which is measured in grams, of a McDonald's beef Sammy. I'm going to abbreviate it, let's call it Sammy. So don't forget to say that word predicted. Y hat is the predicted fat in grams of McDonald's beef sandwich. And then the X, that's just the carbs in a sandwich. So I just use the quote marks. So I don't have to write the whole thing out again. That's just the carbs. And the X isn't predicted. So those X is actually values we can just plug in. The Y is what's predicted. That's why it has a hat on it. So to avoid having to write all this stuff out every time, which you'll have to do if you write your equation with X and Y and you don't say what the variables are, you have to write it out like this. Just use the fat hat. So the fat hat means you write the same equation, but you just put the hat over the word. So it's predicted fat, and then where the X was before, you just write grams. So that's a really efficient way to get around having to write the equation and then define each letter every time. It's just use the fat hat and then write whatever word is in here that you're predicting, and then grams, just replace that where the X was. So instead of using variables, just use the words from the equation. Okay, so let's interpret the slope and the y-intercept. And this is something we have to be proficient at. So the slope, which was 0.338, I think. Well, that tells us, and since it's 0.335 over 1, so for every 1 unit increase in carbs, which was the X variable, we predict a 0.335 increase in fat. So for each additional gram of carbs, the predicted fat content in grams increases by whatever that number is, 0.335. And then for the y-intercept, remember that's when the x value is 0. So that would be for basically a carb-free sandwich. So 11.814, our y-intercept, means that for a beef Sammy with 0 grams of carbs, right, super low carb sandwich at McDonald's, doesn't exist, but if there was one like that, whoops, getting ahead of myself here. If there was one like that, we would predict it to have 11.814 grams of fat. So that's slope and y-intercept. Being able to interpret those for any kind of line is important for this chapter. Part C says calculate and interpret the residual for the Big Mac. Big Mac apparently has 45 grams of carbs and has 29 grams of fat. So the residual, that's the actual minus the predicted, right? The actual minus the predicted. But right now it's important for you to know which variable we're looking at. So remember we're looking at the y values for this. So the y values for us was the fat. So the actual fat was 29 grams. The predicted fat, I'm not sure. Whatever we predict the fat would be for a Big Mac. But 45 grams was for the carbs. That's not what we're talking about for the outputs. That's not a y value, it's an x value. So the actual fat was 29 grams. We know that. We just don't know what the predicted fat was. So 29 grams for a Big Mac. What would we predict it? Based on the line we just made, what would we predict the Big Mac to be? So that's really simple. Just plug in Big Mac has 45 carbs. That's what we're using to make our prediction. So let's predict the predicted amount of fat for a sandwich with 45 grams of carbs. So just plug in 45 for the grams. The predicted fat, that's an easy calculation, 26.889 if we're using 3 decimal places. So what's the residual? Well, just subtract the actual minus the predicted now that we have the predicted. So that's 2.111. And then we got to make sure we interpret this thing. What does it mean to 2.111? So since you got a positive residual, that means the actual value was higher than what we would have predicted. So that's the point. So the Big Mac has about 2 grams more fat than we would predict based on just using our line. Okay, so now we're moving on to a newer topic. We talked about residuals. Now let's talk about what a residual plot does. So residual plot, that's just a scatter plot of the residuals against the explanatory variable, the x variable. And they help us assess how well a regression line fits the data, or how well a line would describe your data. So essentially we just graph all the residuals for every person in the scatter plot, and we look at that as a residual plot. Okay, so how do you examine these things? Again, here's the truck example. I'm going to keep revisiting that. So there's a bunch of trucks above, there's a bunch of trucks below, and we've already seen the residuals as being just the vertical distances from the line to each point. So if you graph those, like those vertical distances versus their x values, look, notice they have the same x-axis. This one just has residuals. So here's the residual equals 0 line. That would be for the trucks that, like, their actual value was exactly what we would predict it to be. They'd be right on the residual equals 0 line. And then some of them had big positive residuals, some of them had big negative residuals. So a residual plot, in general, it magnifies the deviations, like how far each point is away from the line. And then so it's easier to see any unusual observations or patterns. So it really kind of zooms in on the deviations. Okay, and for a good residual plot, like if a linear model is actually good for that model, or for that data, it should show no obvious patterns, and it shouldn't have very big residuals. So hopefully they're relatively small in size, the residuals. If those two things hold, then yeah, a linear model is appropriate for those data. Okay, so let me scroll down here. Okay, I'll put these on the notes just to give you two examples of residual plots you might see where linear patterns are obviously not appropriate. So residuals are the leftovers. So if you see something like this in a residual plot, or something like this where there's obvious patterns or there's a curve, then that means a linear model is not appropriate. So wherever these data came from, I'm not sure where it was, but a linear model would be not appropriate if you see residual plots that look like this. That should be an alarm that goes off to you. We should see a nice random scatter of points. We shouldn't see any pattern in the residual plot. So what's the purpose in general of a residual plot? Well, that's just another tool to tell you if a linear model is actually appropriate for the data set. So it's another tool to assess linearity. Is it linear or not? Or curved or just nonlinear in general? Along with just looking at the scatter plot and saying, does it look like a linear trend? This zooms in on the residuals, so it magnifies the deviations. So it's another way that you can assess linearity. What do you look for in a residual plot? How can you tell if it's appropriate? Like appropriate for a linear model? Well, basically, if there's a nice random scatter of points, that's good. Like random scatter above and below the line, that means a linear model is acceptable for that data set. If you see obvious patterns like the ones I just showed you where there's a curve, for example, well, then a linear model is really not appropriate. So those are your two checks right now for residual plots. Okay, and then we're going to finish off here with the McDonald's beef Sammys again. It says calculate and interpret R. So maybe your calculator already did this for you. If not, you need to turn on the setting that actually gives you the R value, the correlation. And I'll show you how to do that again right now. So if your calculator looks like mine, it's not spitting out the R value, just hit second catalog, it's 0 down there, and then go to diagnostic on. So starts with a D, so diagnostic on, and then just hit enter and turn that on. Oh, there it is. Diagnostic on, enter, and now when you do this again, so when you go stat calc lin reg, notice it spits out the R value. So we don't want R squared for now. We don't know anything about that yet. We want R. R is 0.2628, that number there. So we'll just keep 2 decimal places, so R is 0.26. So being that R is 0.26, how do we interpret that? How do we interpret that? So that's a pretty low R value. So it's definitely positive, but it's pretty low. So there is a weak, we'd say a weak positive association. There's a weak positive association, and we got to give context. So between grams of fat and grams of carbs for the McDonald's Sammys. So that's what 0.26 means. It's positive, but it's pretty weak. It's not really close to 1. Okay, here's the big question. If you remove the one with 18 grams of carbs, who knows what that is? Probably big and tasty. If you remove the one with 18 grams of carbs, how would the least squares regression line change? And how would R change? Okay, let's go to the calculator, and let's delete the one that has, I think it's the last one, it says 18 grams of carbs. So if I go to stat edit, go down to my 9th one here, yeah. So the one that has 18 we're going to delete, and make sure you delete the other one too. Otherwise you get an error. So now you don't have a 9th entry for L1 or L2. So we deleted that sandwich entirely. Now let's do stat calc lin reg again. Notice you delete that 1 point and the R value goes all the way up to 0.74. So that's a big jump in the correlation. Let me show you what this looks like graphically. Okay, so here's a scatter plot of the McDonald's beef sandwiches. This red one over here, that's the one that's at 18. So right now, this has got the R value equal to whatever it was before, 0.26. And I'll even put the least squares regression line on here. So right now it looks like that. So if we delete that point, I'm going to delete it right now. Now look at the data. It goes right through these, and that's when it gets a lot stronger. Now R is up to 0.74, whatever it was. So you see just how big of an effect that 1 point had. I'll put it back on there. So there's the 18-gram sandwich, the big and tasty. And then if you delete it, correlation gets a lot stronger. The slope of the line goes up. So now we got this new line and a stronger correlation. So what can we say? Well, you saw in the calculator we have this new LSRL. If you delete that 1 point, predicted fat is 1.694, that's our new slope, and we got a new y-intercept. And then more importantly, our correlation got a lot stronger. Now it's 0.74. You could even call that a strong positive association. So the two things that happened, one, our line changed, our slope increased, and the strength of our correlation and our linear association obviously increased. All from that one single point. We got a big jump in the correlation. Okay, so the last thing we need to do on these notes is construct and interpret a residual plot for the McDonald's data. I'm going to show you how to do that in your calculator, because I know you can take the residuals and do it one at a time by hand, but it's a lot quicker to do in your calculator. Okay, so since you already did linear regression on this stuff, let's go to, well, first let's put that point back in. So that was 18, 1828 was the final point there. So let's make sure that that's there. So 18, and then over here was 28 grams of fat. Okay, and then if you do stat, calc, lin, reg, whenever you do this, your calculator stores data about this. So once you do this, it stores all the residuals. It stores all the residuals. So we're going to make a stat plot. So hit second y equals, plot 1, turn it on, make a scatter plot. And now here's the key. Your x list is still L1, but your y list, I want you to make it the residual plot. So here's the trick. You hit second stat. That's your list option. And then go call up the residual list. So resid. And that's where your calculator stored all the residuals already. So your calculator screen should look like this. X list L1, Y list is residuals. And now I'm going to graph it, but just so I make sure I can see the window, I'm going to hit zoom 9. That's zoom stat. And there's my residual plot. Okay, so which person is which on here? Just hit trace. Hit trace, and notice how it highlights an individual. So that's 31 grams of carbs. It has a residual of -13. And then just click the arrows, and it'll highlight which one is which. 33 grams of carbs, -10. Let's keep going. 34 is almost right on the line. Keep going, keep going, keep going. All of them are on here. You can probably tell which one's 18 over here. Residual is +10. So this is what we're going to use to make our sketch. So first thing I need is some axes. And then since we went on the x-axis from, I think 18 was our lowest and 45 is our highest. I'll just count by 4s here. We'll go 16 to 44. And that'll include just about everybody. And then from the residuals I saw, we can go from 20 to -20 on the y-axis. So let's be really careful what our axes are. This is the same axis we use as in the stat plot, the scatter plot. So those are our x values. So that's carbs in grams. This line, that would be the 0 line. So that's an important place. That's like when our residual equals 0. That's that line right here, like our x-axis. And then the y-axis, what is that? Well, those are actually our residuals. So this is how you make a residual plot. You just sketch the x values against their residuals. So I'm going to put these little gold dots in here from what I saw in the calculator. There we go, there we go, there we go. Okay, and you can use your calculator to make yours a little more precise. It's going to be difficult to just try to emulate mine on your paper. So if you use the residual plot, you can make your sketch on your own. And then if we interpret this, well, this seems decent actually. I mean, there's no obvious pattern. It's pretty random. Obviously there's an outlier, but there's still no pattern. So the fact that there's no obvious pattern would indicate that a linear model would be acceptable. Okay, that's all for these notes. I'll see you in class.